Okay, let's talk about, I guess, hypothesis testing. So on Wednesday, we covered hypothesis testing for a proportion with one sample. Today, we're going to talk about hypothesis testing for two proportions with two samples. So our topic of the day, hypothesis testing for P1 and P2 based on two samples. Based on two samples of data. Okay. And the big idea here is you've got, this represents population 1. Population 1 has proportion P. Or I'm sorry, has proportion P1. And over here, this is population 2. Population 2 has proportion P2. Okay? Like every other example, the populations are too big for us to observe directly. So what do? We take a random sample. Okay, we take a random sample from each of these things. So from population 1, I take a little piece. This is sample 1. It has proportion P hat 1. Okay, and from population 2, we take a little piece. Over here, I have sample 2. And it has proportion P hat 2. And the question is, if P hat 1 is different from P hat 2, which is almost certainly the case, P hat 1 and P hat 2 are different, are different from each other. Does that mean that P1 and P2 are different? Or is it possible that P1 and P2 are the same, and the reason why we got different P hat 1 and P hat 2 is because of random sampling, okay? And it was just random sampling that produced different P hats. Okay, and that's kind of what we want to answer. We want to know if my P hats, P hat 1 and P hat 2 are different, does that mean that the respective populations have different proportions, or is it just random sampling that's behind this? Okay, and so to do this hypothesis test, we follow the same 4 steps of hypothesis testing. Okay, and so do you remember what those 4 steps or stages of hypothesis testing?
Hypothesis?
Yeah, so the first part is make your hypotheses. The second part is preparation. Third part would be calculation, calculating your p-value. And the last part would be conclusion, making your conclusion based on the p-value that you found. Okay, so let's go through these 4 steps, and then we'll work through an example. Okay, so, part 1, make your hypotheses. Okay, the null hypothesis will be P1 is equal to P2. Okay, or in words, this means the null hypothesis states that the two populations have the same proportion. So that's what the null hypothesis is. Okay, the null hypothesis can also be written as is that P1 minus P2 is equal to 0. So we can also write it as P1 minus P2 is equal to 0. And one thing to note is that the null hypothesis always has an equal sign, right? So this was true last time, it's still true. So this is always true. The null hypothesis always has an equal sign. Okay. So then the alternative hypothesis. What about the alternative? The alternative hypothesis is identical to the null, except we replace the equal sign with something else. So we say P1 is not equal to P2. Or maybe we write P1 is greater than P2. Or P1 is less than P2. Okay? So your choice of not equal or greater or less depends on how the question is written. Okay. All right, and of course, these things can also be written, the alternative can also be written as, the alternative is that P1 minus P2 does not equal 0, or P1 minus P2 is greater than 0, or P1 minus P2 is less than 0. Okay? Okay, so that's the hypotheses. Are there any questions here? Okay, so the null hypothesis, you can pretty much always count on it being this, and of course, and this and these two things are saying the exact same thing. To say that P1 and P2 are equal, that's also saying that the difference between them is nothing, that there's no difference between them. Okay. So you establish your hypotheses, okay, and then the next part is to do your preparation. Okay. So as far as preparation goes, we need to identify the data, identify values in the data. All right. And so what we have is we have sample 1. Sample 1, from sample 1 you need the size, and p hat 1, which consists of x1 divided by n1. This is our proportion. Okay, and then from sample 2 you need n2, the size, and you need p hat 2, which is going to be x2 over n2. So pretty much you need these values. Identify these values in the data. once you've identified the values in the data, the other part of preparation is select your significance level, select or identify, perhaps the problem will tell you what significance level to use. Identify the significance level. Okay, significance level, which is alpha. All right. What's the default level of alpha if we don't see it written in the problem? Yeah, so the default level, default choice for alpha is equal to 5%. Okay, and then lastly, the other part is check conditions to use the central limit theorem. Okay. Because this hypothesis test also assumes that the sampling distribution follows a normal distribution, and if that's the case, that means the central limit theorem must be true. And in order for the central limit theorem to be true, those conditions need to be met. And if those conditions aren't met, our conclusions will not be valid. Okay? You can do a test. Okay? You can go through all of the steps, but whatever conclusion you make, if these conditions aren't met, that conclusion just won't be valid. Okay? Because the assumptions going into it were wrong. Again, for exams and quizzes and things like that, you can assume that the conditions are met. You don't actually have to go through and check them yourself. But in real life, it's important that we check these conditions. Okay, that's the preparation step. And now we do our calculation steps. Calculation. On Wednesday, for the hypothesis test, for a proportion P based on one sample, the steps were standard error, z-score, p-value. Okay? For today's hypothesis test, where we're looking at P1 and P2, it's the same thing. We got standard error, z-score, p-value, except we have one additional step at the very beginning, and so I'm going to call that step 3 AA. Okay? So this is just one step before we do standard error, z-score, p-value. Okay? And this is, we have to find the overall p-hat. Okay? So we need to get the overall p-hat of the problem, and in this case, the overall p-hat is x1 plus x2 divided by n1 plus n2. Okay? So you can kind of see this as total successes divided by total observations, or total sample size. Maybe I'll just write that, total. So you kind of combine the two samples and get the total number of successes divided by the total sample size. You don't average p-hat 1 and p-hat 2. You have to combine x1 and x2 divided by n1 and n2. Okay, now we can do standard error, z-score, p-value. Standard error. Okay. The standard error is just given by a slightly crazy formula. There's not much we can do about it. It's not too terrible, but you have to take the p-hat that we found in the previous step, 1 minus p-hat, times 1 over n1 times 1 over n2. Okay, so we put that in there. So 1 over n1 plus 1 over n2, p-hat times 1 minus p-hat. Everything inside the square root. That's your standard error. Next part, we get our z-score. We can also call this our test statistic. Okay. The z-score is always in the form of the observed minus the expected divided by the standard error. Okay? Let's go back and just recall what the null hypothesis, okay? What was the null hypothesis? The null hypothesis was that, I'm going to write it in this form, P1 minus P2 is equal to 0, right? When we took our data, what did we actually see? What we actually saw for P1 minus P2, we would actually observe P hat 1 minus P hat 2. This is the observed difference that we saw. P hat 1 minus P hat 2. If the null hypothesis were true, what would we expect this difference to be? We would expect that difference to be 0, okay? So the observed minus the expected would be P hat 1 minus P hat 2 minus 0 divided by the standard error. It's kind of silly subtracting off 0, so just the z-score just becomes P hat 1 minus P hat 2 divided by the standard error. So this is our z-score here, okay? But at the heart, it is what we observed, the observed difference between sample proportions. Our expected difference between sample proportions is 0 divided by the standard error. So we're just saying, you know, observed the reality versus the expectation, and we take that difference, divide that by the standard error. Okay, so we get a z-score. Okay, and then once you have your z-score, you look that up, look up in the table, okay, to get a p-value. All right, and do you remember the rules on how the z-score works, or how the how you look it up in the table to get your p-value? It's the same as before. It depends on the alternative hypothesis. All right, and it's the same rules as before, so I'm just going to go kind of quickly. If the alternative has a less than sign, then the p-value is equal to what? Area to left or right of z? Left of z. If the alternative has a greater than sign, then the p-value is equal to the area to the right of z. And then lastly, if the alternative has a not equal sign, the p-value is equal to what? 2 times the tail area. And the tail area is always the area going away from 0. So that's how we get our p-value. So far so good? Okay, it should be very familiar, everything, right? The form, the structure of this hypothesis test. Okay, and then the last part, what do? To make our conclusion, what do? We compare the p-value versus what? To the significance level alpha. And if the p-value is greater than alpha, what does that mean? This means we do not reject the null hypothesis. Okay? And the interpretation of that would be we do not have evidence that P1 and P2 are different, okay? The observed difference between P hat 1 and P hat 2 can be explained by the random sampling process. Okay. That's if the p-value is greater than alpha. On the other hand, if the p-value is less than alpha, what does that mean? That means we do reject the null hypothesis. Okay, and that means we do have evidence that P1 and P2 are different. Okay, or P1 and P2 are different, or we do have evidence to support the alternative. And, or we might say, while it is technically possible for random chance to produce, you know, p-hats that are as different p-hat values that differ as much as our p-hat values. Okay, it is unlikely to happen. So while it is technically possible for random chance to produce p-hat values that differ as much as the p-hat values that we saw, it's unlikely to happen. Therefore, we conclude our values are not from random chance. Okay? Are not a result of chance alone. All right, is this all good? Yes, question?
What does it mean by you have evidence to support each?
So if our alternative was that P1 and P2 are, that P1 is greater than P2, then we would say we have evidence to support that P1 is greater than P2. So whatever the alternative hypothesis states, we would say we have evidence to support that alternative.
So the above one doesn't have anything to do with alternative?
It does. We would say we don't have evidence to reject the null.
Right.
And we would say we don't have evidence to support the alternative. Okay? If we wanted to further that. Okay, then let's try working through an example here. Okay, so we will, what we need to do is we want to compare the proportions from two samples, okay? So let's say, you know, we wish, this is our problem, okay? Example problem. We wish to compare the proportion of senior citizens living in, we'll say, 2 neighboring counties. All right. So we want to know, do these 2 counties have different proportions of senior citizens or not? Okay. So let's say we go to county county A, okay, and somehow we get a random sample of people. So we'll say a random sample of 100, we'll say 160 people. Okay, so we get a random sample of 160 people, and we will say 42 of them are seniors. We'll define seniors as what, 65 plus? I don't know. Okay. County B, okay, we'll say somehow we get a random sample of 120 people. 26 of them are seniors. Okay, and so we want to, our question is, does our data provide evidence that the proportions of seniors are different for the two counties? Okay. All right. We'll make a clicker question here. So the clicker question will come up with your hypotheses, and specifically, what is the alternative hypothesis? Okay, and so your choices for alternative hypothesis will be P1 does not equal P2. Alternative hypothesis will be P1 is greater than P2. Alternative hypothesis, P1 is less than P2. And D, our other alternative hypothesis will be that P1 is equal to P2. Okay, go ahead and go through that. You can discuss with your neighbors if you need to. Okay, what is the alternative hypothesis? Okay, let's take a look. And the correct answer choice is A. Okay, so when we set up our hypotheses, the null hypothesis is going to be P1 is equal to P2. This is our null hypothesis. The null hypothesis is that they are equal. The alternative is going to be P1 something to P2, okay? And because the question just says, are they different, okay? Here, different would imply not equals. So we're going to use the not equal sign. So that's going to be our answer choice here. If it said, does our data provide evidence that the proportion of seniors in County A is larger than the proportion of seniors in County B, or that County A has a higher percentage of seniors than County B, then we would be dealing with a directional one, and in that case, County A, we would say proportion for County A or County 1 is greater than the other one. P1 is greater than P2, something like that. Okay, so depending on how it's written. You would never have an equal sign in the alternative, okay? You always have an equal sign in the null hypothesis, never an equal sign in the alternative. All right, we'll continue on. We'll do our preparation. Okay, so preparation involves identifying the data. The data pieces, okay, and so we have sample 1. We'll call sample 1 will be County A, and sample 2 will be county B. Okay, so our N1 is 160, and P hat 1, which is X1 over N1, is 42 divided by 160. We get P hat 1 equal to 0.2625 if I punch this out into the calculator, I'm pretty sure. 42 divided by 160. Yep, okay. Sample 2, what's N2? That's right, 120. And P hat 2, X2 over N2, what do we write? 25 divided by, or I'm sorry, 26. I forgot what I wrote. 26, right? 26 divided by 120, 26 over 120, 0.21667, okay? 21667, okay. So that's P hat 2. Okay, we would select our significance level. One wasn't specified in the problem, so we will use alpha is equal to 5%. And then we would check conditions. In the interest of time, we will just say conditions are met, okay? But, you know, random, large sample, yes. Random samples, large samples, we have at least 10 yeses and at least 10 nos. Big population, assuming these are not tiny counties, it's possible, but big population will be met, okay? So we'll say these conditions are met. Now we'll go through and do our calculations. So we have to get the overall P hat first. Overall P hat is X1 plus X2 divided by N1 plus N2. Okay, so in our case, we would take the overall number of yeses in sample 1, 42, plus the number of yeses in the other sample, 26. And we're going to divide by sample size 1, 160, plus 120. Okay? So I get a total of 68 divided by 280. 68 divided by 280 gives me an overall proportion of 0.242857. 0.242857. So that's my overall P hat. Okay. So far so good? And then now I get my standard error. The standard error is given by the formula P hat times 1 minus P hat over 1 over N1 plus 1 over N2. So this is going to be the square root of 0.242857 times 1 minus 0.242857 times 1 over 160 plus 1 over 120. Alright, so this takes a little bit of time to punch in the calculator, but I'll do it. 242,857 times parentheses 1 minus 0.242857, close parentheses times parentheses 1 over 160 plus 1 over 120. And I take the square root of that, and I get 0.0518. Something like that. 0.051, we'll say 78. Something around there. Okay, there's my standard error. Now what? Z-score, right? Z is going to be p hat 1 minus p hat 2 divided by our standard error. P hat 1 we found on the previous slide. Well, I mean, I could just put it in fractional form. 42 over 160 minus 26 over 120 divided by my standard error of 0.05178. Or I could put them in decimal form. 0.2625 minus 0.21667 divided by 0.05178. Alright, when I do this, I get a z-score of 0.885. Okay? Our z-table only goes to 2 decimals of precision, so, you know, we round to 2 decimals. And so we have z is equal to 0.89. All right. Is that good with everybody? All of this stuff? Getting to our z-scores. Z is 0.89. All right, let's do a clicker question here. Okay, so what we have is z is equal to 0.89. And the question is, what is, I gotta look this up. The question is, what is your p-value? Okay, so let me give you some choices here. A, B, C, and D. Okay. Okay, I have 0.8133. I have 0.1867. I have this times, I have, we'll say 1.6266 and 0.1867 times 2. 0.3734. Okay. Okay, so your z is 0.89, yeah. All right, let's take a look here. Okay, and indeed, C is the correct answer. All right, so we have z is equal to 0.89. If the determination of the p-value depends on the alternative hypothesis. The null hypothesis was that p1 is equal to p2. The alternative has a not equal sign. Okay, so alternative has not equal sign, so the p-value is equal to 2 times our tail area. All right, what is the tail area? Well, we draw our picture. Tail area is always the side going away from 0. So if I write 0.89 here, the side going away from 0 is over here. So this is my tail. So the tail is equal to 1 minus 0.8133. My tail is 0.1867. That's my tail. And I want double that. So effectively what I'm doing is I'm saying I want either being more than positive 0.89 or less than negative 0.89. So my p-value is equal to 2 times the tail, and we get 2 times 0.1867, 0.3734. That's our p-value. Okay. Keep in mind, a p-value is a probability. P-value is a probability. It's the probability of your data. So it can never be over 1. So if you doubled the other side, that wasn't your tail, you're going to get a value greater than 1, and you know that's wrong, okay? Because the p-value is a probability. You cannot have a probability larger than 1. Okay, and so we have our p-value, 0.3734, and so now the question is, what is our conclusion? So our p-value is equal to 0.3734. Our last part is make the conclusion. Okay, so we compare p-value to alpha. Okay, we have alpha equal to 0.05. So what we have is our p-value. P-value is greater than alpha. What does this mean? This means we do not reject the null hypothesis. Okay? So we would say we do not have evidence that the proportion of seniors is different for the two counties. Do you guys recall, back from chapter 5, we said, are two things independent, right? And we said, basically, if the probability of A given B, if that's the same as the probability of A, or something like that. So before, we would have looked at our two proportions, and we would have said p hat 1, the proportion of seniors in county A is 0.2625, and the proportion of seniors in county B is 0.21667. We would have said, oh, those things are different. That means the proportion of seniors depends on which county. And we would have said they're not the same, so they are dependent. But now we have an actual test. Someone's talking back there, and let me have you be quiet, please. Now we have an actual test that says, we have different proportions. Does that actually mean that the proportions are different? And when we went through the process here, we found out that no, those proportions could just be a result of random chance. So let me just kind of write that down. So what we will write is that even though p hat 1 and p hat 2 are different, okay, 0.2625 versus 0.21667. So even though p hat 1 and p hat 2 are different, that difference could be explained just from the random nature of the sampling process. That difference can be explained by the random nature of the sampling process. Okay, so we would say, at this point, we do not have evidence that the proportions for the two counties are actually different. Okay. Okay, we'll end there for today. Oh, question?
What's the quiz on here?
The quiz will cover the confidence intervals and hypothesis tests for proportions. So second half of chapter 7 and chapter 8. Okay, I'll post a practice quiz online this weekend, and you guys can take a look also.